In this clip and the next one, we will look at a couple of quick corollaries of the rank nullity theorem. So these both tell us about when maps can be injective and surjective. And so the first one is for looking at maps going into a smaller space. So suppose the dimension of the codomain is smaller than the dimension of the domain, and we'll assume that these are both finite dimensional vector spaces. So if T is a linear map then from V to W, then since it's mapping into a smaller space, there's no way that T can be injective. And so the proof of this is just to use the equality that appears in the rank nullity theorem, that equation. So for a linear map T from V to W, if we solve for nullity in that equation, the nullity of T is going to be the dimension of V minus the rank of T. So that's by our rank nullity theorem. And then that's going to be greater than or equal to the dimension of V minus the dimension of W. And this follows because we have, well, actually here, let's write it as, in terms of dimension, the dimension of the range of T is less than or equal to the dimension of all of W, because the range of T is contained in W. And so this is actually, I'm using proposition 238 for that inequality right there. And then we're assuming that the dimension of V is strictly greater than the dimension of W, so that means that this is strictly greater than 0. So if the nullity of T is strictly positive, in other words, if the dimension of the null space is strictly positive, that means it's not the 0 space, and so it contains things. And then by 316, which characterizes injectivity in terms of the null space, we are done. Okay, so the idea that you should have in mind here when thinking about this result is that to be injective, look what T does to a basis. T must map a basis to an independent set. If it maps it to a dependent set, then you can set up you can use that dependence relation to show how two things get mapped to the same point. And oops, I forgot to finish the sentence. Independent list in W. And to see that, see the claim in the proof of 322, the rank nullity theorem. That claim says that T maps a basis of one to a basis of the other. So for injectivity, all we need is to see that the result is independent. But what you should, the best way to think about this is to visualize it in terms of finite maps, or sorry, finite sets, maps between finite sets. So suppose we just have a basis of V that looks like this, and then suppose the largest, suppose W has a strictly smaller dimension. Well, then that means that the largest independent set you can have in W has two elements. And so then what you're trying to do is you're trying to figure out how to map basis elements from V to an independent set in W in a non overlapping way, And then very soon you figure out that there's no way to do it. So it's for exactly the same reason that you cannot have an injective function from a set of 3 elements to a set of 2 elements, that you cannot have an injective linear transformation from a vector space of dimension 3 to a vector space of dimension 2. It just doesn't work. You run out of places to put stuff. And then we have a nice immediate practical application of this one. So one of the nice things about linear algebra is that even though it looks mind-blowingly abstract at times, it has very practical applications that are right near the surface. And so here's kind of our first example of that. If m is strictly less than n, then a homogeneous system has non-trivial solutions. And so here the homogeneous system that I'm looking at has m equations in n unknowns. So we'll call it coefficients a11 x1 up through a1 m xm, and it's homogeneous, so that has to be equal to 0. So there's our first equation. And oh, excuse me, I put m's instead of n's. N variables. And then there's m equations. Okay, so we've got a homogeneous system of linear equations where there's m equations and n unknowns. And we're saying that if m is strictly less than n, then it will have non-trivial solutions. Oh, and in case it's not clear, these are all scalars. So the proof for this is pretty straightforward. We just rephrase it in terms of linear maps. So define T as an element from Fn to Fm by saying that T of x1 through xn is, and then here we put the equation. So here's the first thing that's set equal to 0. So a1k x k, and then down to the last thing, mkxk. So I'm taking, let's see, this guy here, I'm putting that in for my first one, and then I'm taking this guy here and putting that in for my last one, like so. Okay. Then T is not injective by the thing that we just proved. So the nullity of T is going to be then strictly positive. And so those things that are in the null space, those correspond to multiple solutions for the homogeneous equation.